SwayamPrabha. Digital India. Educated India.
Welcome to the lecture and the last lecture of the lecture series on mineral resources, geology, exploration, economics and environment. Since this lecture recording is actually going on much before before that you people would be going through these lectures, so we know that there will be many things that will be coming up in between for discussions, and many of the things that would be needing clarifications, but it has been a long journey. So before we come to the close of this lecture series, let's discuss another very important aspect of mineral resource exploitation. Although these subjects would better be discussed by people who are better experts on this, but since this is a first level course on mineral resources, it's important, it's worthwhile to go to discuss this aspect here. And this has been one of the issues, burning issues, not only a national but an international issue, which actually pertains to the environmental impact of exploitation of the nuclear energy resources, or the problem of the radioactive waste disposal. Many of us right from our childhood have been hearing about these issues, about the effect of the radioactive material being dispersed into the atmosphere, to the environment, to our habitation in various ways, and we all grew in situations and where we always think of the possibility of a nuclear explosion and the accidents in a nuclear reactor, or the worst possible case of a nuclear bomb being used by anywhere in any corner of the world. With many of us born even after the Second World War, which has the bad memories of the atom bomb in one of the countries of the world, we all know. So the situation is that we need the resources for nuclear energy, for energy generation, and if we think that the fossil fuel resources, which essentially are used for generation of electricity, amongst the non-renewable resources like coal, petroleum and natural gas, there will be eventually there will be the more and more use of nuclear energy, and there will be more of such nuclear reactors producing energy for our day-to-day requirement, and our energy demand is always on the rise. So then we are using these minerals, which are the resources for nuclear energy. We all know them, that they are uranium and thorium bearing minerals present in many types of deposits, which you have seen in our course of discussion on the mineral deposits, all the uranium bearing deposits, and the thorium being mostly enriched in the form of the monazite sands and as mechanical concentration deposits in the form of beach placer. So we are talking about, so these mineral resources are utilized for generation of energy in nuclear reactors. So let's first have a look as to as a matter of general knowledge for all of us, that what actually is known as the nuclear fuel cycle. So here this is the diagram. This is the nuclear fuel cycle being represented here. So the nuclear fuel cycle actually starts with the mining of uranium ores, whether it's any type of ore where the uranium ore is being mined. And we all know that even the richest of the uranium mine that we know, hardly 1%, 1.5 or 2% of U3O8, and in most of the cases, like for example the Indian deposits where the uranium concentration in form of U3O8 goes to 0.04 or 0.06%. That means 0.95 or 0.94 or 0.96 part, or 95 to 96% of the 95.5 or 99.54 or 99.6% of the material is actually the waste. So in the mining itself, anywhere there is a uranium mine, it will always be considered as a source of radiation in excess of what is the background radiation, and then these uranium the uranium ores will be mined from the mine and eventually need to be processed or milled for enrichment or for the extraction of the uranium in some form. So the extraction has to follow a certain route, like we discussed before. When they occur in silicate rocks, they can be very well acid leaching process is set up for extraction of the uranium. If they occur in carbonate kind of host rock, then some kind of alkali leaching kind of process is set up. In any case, there is going to be a process in which the uranium metal has to be extracted in some form which will be utilized. So that is in the process of milling, what happens is that when 99.5% of the material, in case of the uranium deposits which we see in our close periphery, so there 99.5% of the material will be discarded in the form of tailing, as we have seen before in case of multimetal sulfide deposit. So here the tailings are there the concentration is not reduced to zero, so they do have some amount of the radionuclide present in them. So whenever they are accumulated in huge quantity in the tailing dam, then they are also a source of radiation which is in excess of what is the background radiation. In addition to that, whether it's a uranium mine being worked out or whether the tailing dam, there is one major issue that comes up sometimes is the emanation of the radon, which is a gas which comes out from the disintegration of the uranium radionuclide. So that radon by the radioactive disintegration of U-235, so that radon which we'll be seeing in a short while, so that is believed to be toxic or believed to be rather carcinogenic, known as causing lung cancer in people, allegedly. I mean, it's physiologically not very well proved, but there is a belief. So once the milling is done, then this process of extraction takes place from the leachate, from the concentrate. This process of extraction, as I said, goes by the process of acid leaching by use of a series of the chemicals which are also discharged or effluent to the surrounding. And what is obtained in this process of the extraction of the metal is something which we know as yellow cake, or the diuranate of magnesium or sodium, because once they are treated with some acid leaching kind of process, then for their conversion they have to be again reprecipitated back by some chemical process, and they are finally obtained in the process of magnesium or sodium diuranate, or the yellow cake. And that's a yellow cake which now we all know that it's a mixture of uranium 238 and 235 in a proportion of 1:137.8. So roughly very small percentage of the small proportion is actually U-235. That's the radionuclide which is the target, because that undergoes the fission reaction to release the energy. That's what we are looking for. So here there has to be some process of enrichment of the original material where to at least increase the proportion of the U-235 to some extent, and that is done by the process of in a solid, because their mass U-235 and U-238 are so very close. So by physical in the solid state, the enrichment process will be rather difficult. So they are converted to their hexafluoride state in a gaseous state, and by which they can be, there's some kind of a selectively permeable membrane is used, where the diffusion of the U-235 is possibly controlled, where the material could be obtained with a little higher proportion of U-235 compared to what was originally present. And they also could be put into some kind of ultracentrifuge, where the U-235, these two, the material could be enriched with respect to U-235, and then these material are formed into the pellets, made into pellets by sintering, and put into they're basically the pellets which are made out of the product which after the enrichment process, and they are put into fuel rods and into fuel assembly, and the fuel assembly is put into the nuclear plant, where there are controlled fission reaction which goes on with use of moderator like lighter element or heavy water or graphite which are used as moderator, and then the energy is liberated. And finally, so once the fuel, so here these pellets which are put into the rods, and that makes basically the fuel assembly, and that fuel assembly which is put into the reactor, core of the reactor, where the controlled fission reaction take place and the energy is liberated. So here you could see that the energy is liberated by the process which is known to us by making by heating the water in the form of steam and making a turbine move, and the electricity is generated here. And then, but what remains is basically that these kind of fuel assembly, the fuel rods in a nuclear reactor, they stay for about 2-3 years, and then they have to be by the time they become inefficient, or the energy that is, they become less energy producing, or they have to be discarded, or they have to be discarded from the reactor. So once they are discarded, if in a stage that they cannot be used any further, then they are basically the waste material, which are the spent fuel. So they are the most the materials of most concern to us, that they are this spent fuel, and they have to be discarded. So before they are discarded, the spent fuel, as will be going into a little bit of details, they do contain lots of short-lived radionuclide, and they are highly active and very hot and producing lots of heat energy. So immediately they cannot be disposed of to the environment. They are stored in pools, water pools for dissipating the heat, and also most of the short-lived radionuclide to actually disintegrate and reduce their concentration to a substantial proportion, and then finally, but ultimately these spent fuels have to be disposed of, disposed of somewhere in some form, but then with a major concern remaining that they will always be posing threat to life in general, no matter where they are being disposed of, whether they are in the deep in the ocean or anywhere. So there are some ways that this fuel rods, after they are actually taken out from the reactor, they again can be reprocessed and for many other purpose, and then could be finally reprocessed and recycled, and there could be many intermediate process which can go on depending on what the purpose is. So we will not be discussing about details of the different types of reactors, like the pressurized heavy water reactors or the fast breeder reactor, etc. Will because of lack of time, but one can always see what they are for the general idea. So this is what is essentially the nuclear waste. So whatever is coming out now here in this process, the waste which is generated as the tailing in the process of milling is actually radioactive waste. But we know that there in terms of the concentration of the radionuclide is low, so they don't pose that much of threat as the ones which is posed by the spent fuel or any other product that comes out during the process of this nuclear reactor, which we'll see them a little bit. So before we go to the radioactive waste and their disposal, we have some general idea. So we know the units that we use for the radiation dose. So 1 curie is essentially 3.7 into 10 to the power of 10 disintegrations per second, and sometimes the unit which is used for the radiation dose, which is becquerel. So this is actually 1 curie will be equal to 37 giga becquerel, and the unit of exposure dose for X-rays and gamma rays, which is in terms of Roentgen. So 1 Roentgen is 87.8 arcs per second. You could imagine the kind of energy that is released, or 5.49 into 10 to the power of 7 of mega electron volt per gram in air. And the unit of absorbed dose is in rad. So 1 rad is 100 arg per gram. That means equal to 6.25 into 10 to the power 7 mega electron volt per gram. So when it comes to the radiation dose, so in terms of this REM, the Roentgen per equivalent, the Roentgen equivalent for people, which is REM, is essentially a rad, 1 rad, which is 100 arg per gram, or 6.25 into 10 to the power of 7 mega electron volt per gram into a quality factor. That means when it's actually the human beings are getting the dose in terms of REM, it is rads multiplied by the quality factor. So in case of gamma rays or X-rays, the quality factor is 1, whereas for alpha rays the quality factor could be as high as 20. And there are something like, so what is the maximum permissible dose? There are sometimes some empirical formula which is used that it should be 5 into n minus 18. So n would be the age of the person, minus 18 into 5, so that would be the dose. So there are many international regulatory bodies and many laboratories, and maybe sometimes there are some national bodies which also fix such kind of limits, that what could be the radiation dose that a person should be receiving per annum, which could be thought as safe, or beyond which could be unsafe or potentially risky in terms of the health. And we know the health consequences could be anything very drastic as well. So the nuclear waste, the radioactive waste as concerned, so they are either divided into either the low level or high level, or low level, intermediate level and high level wastes. So the low level wastes are the ones which are likely to be having in terms of the total amount of radiation coming the minimum. So they are generally the uranium mine tailings. They are potentially dangerous as landfill. Sometimes there are instances where these kind of tailings were unknowingly used as landfill, on which there were human habitation and construction of houses, but they finally have to be demolished because once it was observed that they are emanating huge amount of radon, and those radons are actually accumulating in the air in the houses and posing serious threat to the to human life. And there are instances in the past where such kind of habitation have to be totally demolished because of this problem. So the large volumes of waters that come from the nuclear plants. There are laboratories and hospitals which also use this radionuclide for medical purposes, and their wastes, contaminated lab equipment, protective clothing, and the animal parts. So these are the low level wastes, and their disposal also the strategy is a little different. They could be stored, could be put into some kind of trenches, and could be put in solid concrete and put into the sea, as has been done in the past by many countries. So there are these are essentially low level wastes, and there are intermediate level wastes, which are the materials which are used in nuclear power plants, like flasks used to transport fuel, various liquids used in the plant, contaminated rags, tools, clothing, etc., the spent filter cartridges, spent demineralizer resins. So because these kind of demineralizer resins and these cartridges are used for recovering the radionuclide from the liquid waste in the nuclear power plant, and those are also considered as intermediate level waste, where the radiation is higher than those which are considered as low level. So in terms of quantity, if we see, so now the high level wastes are essentially the spent fuels, the large quantities of liquids, the used fuel rods. Actually, the volume wise, the high level wastes actually are about 0.1% in total volume of the total radioactive waste that are produced, but they account for 95% of the total radiation. So as we know that they are the spent fuels, they are high level waste. So major concern lies with these kind of radioactive waste. So if you could look at what happens to a situation as a comparison for these high level wastes. So this composition of the spent fuel rods from a light water reactor. So if the initial fuel, as we all know that the concentration of this U-235 was raised to about 3.3% by process of enrichment, by conversion to UF6 and centrifuging them, or through diffusion through a semi-permeable membrane. So U-238 is 96.7%. So by the time the fuel could be called as a spent fuel to be discarded, the U-235 was reduced to 0.08% and U-238 to 94.3%. But you could see here that some transuranic elements, the actinides, their concentration has gone up to 0.65%. They are the short-lived radionuclide. U-236 or to 0.46%. The plutonium isotopes or to 0.89%, and the fission products, when they are all zero at the beginning and the initial fuel. So they have obtained such kind of concentration, very high concentration level, which are considered as the high level waste. And these are essentially the as you could see here, if not the full range of the radionuclide that are present in a spent fuel, some range is shown. So here the isotopes, the radionuclides that are generated in a fuel assembly, in the fuel rod, by the time the fission reactions, controlled fission reactions are over, and the fuel can be called as a spent fuel, there the cobalt 60, which has got the shortest of the half-life, which is 5.2 years, and as long as the highest one is the uranium 238, we know what is the half-life of it. So now here we could see that something like we can call as a short half-life, which is within less than 31 years, which up to cesium 137, and after that the radionuclides, americium 241, radium 226, carbon 14, plutonium 239, they do have a much longer half-lives. So that means these fuel rods, the spent fuel rods, even if they could be stored in some places for like in a pool for a good number of years, then many of the radioactive nuclide will be their concentration would be diminished. If we could look at a diagram like this, which has been taken from the Nuclear Energy Agency. So here this is also a schematic diagram. So this is the decay in radioactivity of high level waste from reprocessing 1 ton of the spent this is pressurized water reactor type of reactor fuel. So if the initial radioactivity, so this green line is actually the actinides, and we could see that their activity is falling to very low values within time of 1 million years, and what we could see, so within about 1,000 years the activity is actually decreasing by 4 orders of magnitude. So this, the black line, is actually for the total. So the spent fuel, just initially once it is discarded from the nuclear reactor, whose radioactivity in terms of gigabecquerel, which you can convert to curie, is nearly about 10 to the power 7, bit less than about 10 to the power 7. So this is decreased to almost 4 orders of magnitude within a time span of about 1,000 years. And if they are reasonably stored somewhere about for 100 years, generally they are stored for about 30-40 years for the activity to actually significantly come down by an order of magnitude or so. But then this diagram shows that the activity is very much there, even we take time of the order of 10 to the 1 million years. So then the fission products have short half-lives and higher activities. So actinides have a longer half-lives. The actinides are the 15 elements within atomic. So these are the transuranic elements from 89 to 103. So this gives an idea that, well, the spent fuels, they definitely pose a good amount of threat to the environment, and then the disposal of these radioactive waste is a major concern. So there are many regulations, there are many ways people think of how to dispose them of. Possibly one of the choices is that maybe they could be buried in the deep in the deep ocean, where they'll be get buried in the ocean floor sediments, and they can be there. Or there could be deep geologic burial sites. These are very interesting things, and here the role of geologists also comes very important. There are two examples. In the case of the deep geologic burial sites, they could be either in salt domes, because of the reason that salt domes are dry, they don't have much of fluid in them, and these radioactive this discarded radioactive waste, they need to be put in some place where they should be free of fluid, because fluid can carry or dissolve a lot of this radionuclide and can disperse them into the water. And there are many such calculations, because even if this high level waste, like for example these fuel rods, even a very little of them, if they are dispersed to the atmosphere, they will be almost be equivalent to almost more than a year dose for the whole population. So there are many such calculations, and from that the magnitude of their effect on human beings can be imagined. Salt domes were one of the places where people explored as to put them. But anyway, whenever these discarded fuel rods are just not discarded in this way. They are put into structures which are called the canisters, which are cylindrical kind of barrel, which are made into a very complicated structure where they could be very properly sealed, and then they are disposed of, or they are finally disposed to the to wherever disposal site that one might choose. So salt dumps were for some time one of the favored locations for disposal of these radioactive wastes, but then ideas also came that no, salt dumps also do have fluid inclusions in them, or sometimes they do have very briny fluid which are entrapped in them as pockets, and they are not that very free of danger. So crystalline rocks, like for example a granitic terrain, that would possibly be one of the choices for storage or for disposal of this kind of radioactive waste. So one such interesting example can be cited, that there is a place called the Yucca mountain range in Nevada in United States, where all sorts of scientific work was done, and that particular mountain range, Yucca mountain range in Nevada, was found out to be suitable for disposing this high level waste, for these fuel rods to be put in canisters. And there are many such kind of structures also were designed in terms of galleries, that there's some tunnels kind of things to be drilled through that, and these things to be disposed of. But there have been lots of politicization of such kind of disposal of the high level waste. It possibly is true for any country in the world where there are concerns, very serious concerns are expressed, and when it comes to the disposal of this kind of high level radioactive waste. So without getting into any further details, which can be seen in any source, which are very open these days, and any open or any public domain knowledge or sources of information are there for what is happening even in the situation. It can only be said that a very consensus or a unanimous decision, or a very foolproof or the safe mechanism for disposal of this kind of radioactive waste is yet to be agreed upon. But then the fact remains that yes, we have to be, will be exploiting our nuclear energy resources for generation of electricity till the time that we possibly have a more safer, more clean resource, energy resource for ourselves. Thank you so much. So that brings us to the end, or to the end of this lecture series. It has been a long journey, starting from the scientific principles of formation of mineral deposits, to exploration, to economic aspects and the environmental. Some of the concepts have been intentionally exposed, which may not be covered in very fundamental textbooks on mineral resources, but this has been done with a purpose, because this is the time that from this stage, if we get exposed to certain things, that we possibly the interest will be generated to learn them, and they are interesting areas for higher studies as well as research. And so thank you all, and I'll definitely look for feedbacks from all of you, and thanks again.